Good day. In today's experiment, we're going to verify that the total linear momentum in an isolated system remains a constant. The apparatus that we will use are two trolleys, a dynamics track or runway, measuring tape or meter stick, and a mass meter or any other measuring instrument to measure mass. I am Veena Maharaj. I'm from the Department of Basic Education. Today we are going to conduct an experiment to verify that the total linear momentum in an isolated system remains a constant. Before we conduct the experiment, we need to recall a few things. Firstly, what is momentum? Momentum is the product of mass and velocity. So if we look at the apparatus that I have in front here, you can see I have two trolleys, I have a dynamics track, and I also have some other mass pieces here on the side. So we're actually going to move these objects to give them a certain velocity and study the momentum of these objects. Momentum, since it is the product of mass and velocity, it is a vector quantity because velocity is a vector quantity. The direction of the momentum is the same as the direction of the velocity vector for that particular object. Secondly, we need to choose a sign convention then, since momentum is a vector quantity. In this particular experiment, we will choose my right-hand side as positive and my left-hand side as negative. So that will be our sign convention. Thirdly, what is a system? A system is a small part of the universe that we are considering while we are solving a particular problem. What is an isolated system? An isolated system is one in which the total or the net external forces acting on that system is zero. The word isolated and closed can be used synonymously. They mean the same thing for us in mechanics. Now the apparatus that we are going to use in this particular experiment are two dynamics trolleys here. As you can see, they have wheels for them to move on this dynamics track. We have a dynamics track here, we have a mass meter, we have measuring tape, and we have some extra mass pieces. Now we need to isolate this system. That means there should be the total net external forces acting on the system should be zero. We all know that that is almost or near impossible to attain, but we try our best. We're using a dynamics trolley here that is quite smooth and free of grit to minimize friction, which is one of the forces that can affect our results. Secondly, I used some pieces of paper here under the dynamics track to level the track to make sure that it is horizontal and to ensure that there is no component due to the force of gravity acting along the plane in which the trolleys are going to move. We are going to simulate an explosion here. In other words, the force that is going to cause the trolleys to get into motion is going to be an explosive force. We're going to simulate that by using a spring-loaded balance here, a spring-loaded trolley. If you see, if I hit this, the plunger shoots out and it can strike the second trolley, and that would be our explosive force. Now, as we look at the two trolleys in position, they are at rest, which means that the velocity of each of the trolleys is zero. That means the momentum which is P is equal to mv, that momentum is also 0. The momentum of each of the trolleys is 0, so the net momentum or the total momentum of this system of 2 trolleys is 0. Now, what we're going to do first, we play around with the trolleys, we place them at a particular point, and we simulate the explosion. And what we are trying to do is we want the trolleys to strike the barriers or the ends of the track at the same time. And I'll tell you just now why we want to do that, but let's just see first what happens. Okay, they didn't hit at the same time, which means we have to do that a few more times, but I'll leave that to you. And let's try and get a position now where we know that if they experience the explosive force from this position, the 2 trolleys will strike the ends at the same time. Now, why do we need them to strike the ends of the track at the same time? Because velocity is equal to delta x over delta t. Its average velocity is equal to delta x over delta t. In this case, since we have minimized friction, and we will assume that there is no friction acting on the trolleys when they move apart after the explosion, and that the net external forces on the trolleys after the explosion is 0. That means that the trolleys will continue in their state of motion forever and ever. So that means the velocity of the trolleys after the explosion remains a constant. So actually our average velocity then becomes our actual velocity of the 2 trolleys, and that will be the change in position divided by the duration of motion. Now, we want the trolleys to strike the ends of the track at the same time, so that the duration for trolley number 1 is equal to the duration for trolley number 2. The reason we want to do this is that we can actually then ignore the time, or we can set the time to a unit value of 1 second, because we are not actually intending to measure the actual momentum of the 2 trolleys after collision, but we simply want to verify that the total linear momentum is 0 after the explosion. Now we can simulate the explosion first, or we can take the masses first. I choose to take the masses first. Before I take the masses first, we have marked the trolley as trolley number 1 and trolley number 2, so that we don't get confused with the data for each of the trolleys. I'm going to switch the mass meter on, wait for it to stabilize and read 0, and then we put the mass on it. This is trolley number 1, and its mass is 608 grams. So I'm just going to write that. 608 grams. And then we measure the mass of trolley number 2. Which is 598 grams. Okay, we switch off the mass meter so that we save the battery life, the mass of the mass meter. Now I'm going to set the trolleys back in position, make sure that they're running freely on the track, and then we simulate the explosion. Okay, we mark the points of the trolley number 1 and trolley number 2 as the starting point, the point of 0 displacement, and then we simulate the explosion. Okay, they hit the sides at the same time. So we then measure the distance moved by each of the trolleys. Trolley number 1 moved a distance of 42 centimeters, and trolley number 2 moved a distance of 42,5 meters. Okay, let's just check if I have that correct. It's more like, yeah, 42,5. So delta x1, 42 centimeters, delta x2, 42,5 centimeters. Okay, we need to repeat that a few times to make sure that we have not made any mistake with the measurement of time and, with the measurement of the distance moved by the two trolleys. In this case, the distance and the displacement of the two trolleys, since they are moving in a straight line, would be the same because the length and the direction of the motion of the two trolleys is constant. The one is moving to my right and the other is moving to my left. The displacement of trolley number 2 is negative, and the displacement of trolley number 1 is positive, okay, according to our sign convention. We can now measure or calculate the momentum of trolley number 1. It's going to be the mass of trolley number 1 times the velocity of trolley number 1, which is remember we said we will take delta t to be a unit of 1 second. So we need to convert the mass. If you want actual values there, it's going to be 0,608 kilograms times for trolley number 1 it's 0,42 meters over 1 second, and that would give us a value of 0,255. Okay, 0,255 centimeters. The momentum of the second trolley, momentum 2, will be its mass times its velocity, which is 0.598 times minus 0,425 over 1, which is equal to minus 0,254 kilogram meter per second. By the way, this here is kilogram meter per second. Okay, and this is 0,254 kilogram meter per second to the right. If we look at these two values, the 0,254 negative and the 0,255 positive, you notice that if we add them algebraically, we will get a resultant of 0. Even if we add them vectorially, because this is a vector pointing to the left on the same straight line as this vector pointing on the right, the two vectors would add up to give you approximately 0. The 0.001 difference between when we add the two, because it doesn't exactly give us 0, we can account for by stating that there could be small errors experimental errors due to our surface not being absolutely frictionless, and perhaps our measurement as well being not absolutely accurate. But this accuracy is quite close for us in the classroom, and what we can see basically is that the trolleys, the momentum 1 plus momentum 2 gives us 0, which was the initial momentum. So basically what we are saying is that the final momentum is equal to the total final momentum of the system is equal to the total initial momentum of the system, and our system is simply the 2 trolleys that are in motion. This was our trolley number 2 that moved to the right, and this was our trolley number 1 that moved to the left. But we should not be satisfied with only one set of results. It is always very good practice to repeat an experiment several times using other objects as well. One could perhaps make variations to this particular experiment by taking another situation and varying the mass. Take a mass piece and place it on one of the trolleys, and then we can make them experience the explosive force. But remember, we will then have to move them around. And if you guess this one is of the larger mass, I would expect it to move the smaller distance after the explosion. So when I'm doing my guesswork, I would probably bring it a bit closer to the end of the runway, and the lighter one a bit further away, and maybe we can just try this. As you can see, it was almost hit at the same time. So it's by trial and error that you will find a point from which you can strike them, and then you measure the displacement of the one trolley and the displacement of the other trolley. Remember to tabulate your results, and each time you repeat it with different masses, you can verify in each case that the total linear momentum before the explosion is actually equal to the total linear momentum after the explosion. And in general, the general form of the conservation law is that the total linear momentum of an isolated system remains a constant. Thank you.